and I'm the National Sales Director for Trumpf here in the US. We really appreciate you taking the time, and I can promise you an exciting journey showcasing the latest in laser cutting technology. This being said, I would like to hand over to our Trulaser product manager, Saleh Kuranta, and her team. Thank you again for joining. Enjoy the webinar, and you and your families stay safe.
Thank you, Stefan. We are so excited and pleased to showcase for you guys today some of our newest technology to the laser cutting portfolio. Helping us today will be Brett Thompson, our sales engineer, Dagmar Hagar, our Trulaser team lead applications, and then Ian Frank and James Gamache, both laser applications engineers. To start, we'll give you a brief overview of the technology, productivity gains you can expect, and the unique attributes. Following that, we'll get into the live cutting and demonstration. Then we'll close, bringing everyone back together for a Q&A. So don't forget to use the question box as we go along. With that, let's get started with Brett Thompson.
Thank you very much, Saleh and Stefan. Great job there for the introduction. So now what we want to do is have a little overview of a couple of the different features and options we want to look at on the 5030 fiber today. So I'm going to step through just a couple slides in a PowerPoint, and then we're going to get over to the more interesting things like the actual machine running. So if you bear with me for a moment, I'm going to go ahead and I'm going to start my video or my presentation here and start with the 12,000 watt laser that we have available on the 5030 fiber now. So in that machine platform, most recently we've gone from 8 kilowatts to 10 to 12. The 8 kilowatt has kind of shifted out of the portfolio, and we focus on the 10 kilowatt and the 12. And as you can see from the chart here, comparing the times to the 8 kilowatt, and that's really what we're seeing, we have pretty substantial jumps. So 26% going from 8 kilowatts to 10 at 11 gauge, and then about the same amount when we move up to the 12. So of course, and that's kind of what would be expected, right? You got more laser power, you're going to cut more quickly. One of the nice things about it, obviously we're going to gain some speed. We're also going to gain some edge quality benefits as well as burr limitation benefits. So you can see here, this is the 5/8 material. If my calipers are accurate, they were calibrated right before the demo started. And there's, with a nitrogen cut, just a tiny little bit of a burr, hardly any. But if we use kind of a special process with all that laser power like we have here, I'm not sure how clearly you can see this, but this is actually using a mixed gas. So 0.5% of oxygen in with the nitrogen, and you get really similar feed rates to what you'd have with nitrogen, but just perfect quality. There's really not even a burr on this piece. So it gives us speed. It's going to give us also some capacity benefits. That's also combined with, as you can see here in my little sticky note on the side of the screen, we have a machine platform that's quite a bit more dynamic. So we increase the machine's ability to move around corners and go around contours by 43%, as you can see from the chart. Really, really substantial. What we also have on this machine is something called active speed control. And we actually introduced this technology last year at FabTech. And really, this is the biggest thing to happen to lasers since, well, kind of the laser machine itself. It's really substantial. And so what I want to do is just kind of touch on what it is and also what it's not. So what active speed control is the first proactive system for dealing with anything that might occur with your materials. Like here, I've got a big old chunk of, looks like 1 1/4 steel. This is really, really good quality. If you look on the surface, you can see that the material is nice and black. This is really, really good stuff. This is probably not what most people are cutting. So this is just a regular A36 that we have, and you can see the surface, it's not nearly as pretty as that other piece of material. Though edge quality, they're pretty darn close. And so really what we need to be able to do is control for the makeup of the material. So maybe there's like a little pocket of silica inside the metal or something, or maybe the surface is a little bit scaled, maybe there's a little bit of rust. We need some system that can automatically control for the sort of issues that typically would occur from running into issues within the material itself. And so what active speed control does that other systems don't is respond to an issue before it actually can form. So before you can see it, we're taking a recording many, many times a second. And based on the information from that recording, we're saying, okay, the cut's okay, or maybe the cut's not so okay. And if the cut's not so okay, what it'll do is it'll slow the laser down a little bit. And that's going to ensure that we're keeping the quality of the part good, but also that we're not losing the part. And as you can see from the chart here on the top, we have kind of 1 through 5 for, the level of actual automation that can be achieved. And we need a machine that can really control all those different variables that are necessary for us to get a good piece of material off of the laser. And that's what the 5 series laser with active speed control gives us, the most automated system in the world. It doesn't reactively respond. So it's not saying, okay, I've lost the cut. Now, okay, I'm just going to go ahead and I'm going to stop cutting here. Maybe I'm going to try to do a reentry. Maybe I'm just going to skip to the next job, or maybe I'm not going to be able to tell at all, and I'm just going to cut sheet after sheet of actually pretty bad material. And those sort of systems have been around for quite a while, including ourselves, the plasma sensing devices. So when I'm cutting along here, do I see, a little plasma flash from the surface? If I do, I can say, okay, seems like there's something wrong with this material. Maybe I should slow down. And if it doesn't sort itself out, it'll stop. That sort of system's been around forever on our machines as well as others. And that is a system that's going to make sure that I'm not throwing away a bunch of metal, but if I'm automating the machine, I've got it hooked up to material handling, material storage, maybe even going right on to a bending process that is itself automated. That is really going to make it so I can only do semi-automated production, not true automation. So active speed control, of course, would say, yeah, something's not quite right on the material. And rather than just stopping and waiting for an operator, it just takes care of it on its own. The other really cool thing about active speed control is what it's also going to do is it's going to say, you know what, this material is actually pretty good. And since it's pretty good, and Trumpf is a little bit conservative when it comes to the parameter sets that we use, we're going to go ahead and speed the laser up past the feed rate. So when you look at a cut speed chart from Trumpf, or you look at a time study that we performed, you're probably looking at numbers on a 5 series fiber laser that are less than you get in production. And so from our production facility in Chicago, where we're running this on, for example, 1/4 inch, we generally see there's about an 8% increase in the actual feed rate. And realistically, this is probably the bigger benefit, because lasers have really gotten quite good. Good optics technology, good stability from the lasers. So the laser's ability to just increase the speed on its own by a substantial margin is something that is really going to help with the ROI of the machine. So let's run a little video that shows kind of those 2 different topics we're talking about, though I say mostly the variations in the materials. So what you're going to see here are all the same material thickness, but just different grades of material. So we're going to be dealing with different alloys of steel. We're also going to be dealing with different surface conditions. So some of it's really clean, some of it's not so much, some of it is even coated. And if you look, you can see that it's telling us that we have an averaged feed rate. And even on this bad material, you can see that the averaged feed rate, so not right now, what is it cutting at, but at the end of the job, accumulated, what is our new feed rate? And it's even pushing us past 100%. And so you see, based on the process stability figure that we're looking at, the feed rate being adjusted automatically completely on its own. So again, this is true automation, right? It allows us to genuinely automate that process because the laser can take care of it. You also notice that it was monitoring things like the actual beam center. So since Trumpf uses almost like a clamping system that you have on a press brake where it seats and centers the tools, we use kind of a similar technology for our nozzles, so we never have to align our nozzle to the beam. You only have to be concerned about where the beam is, not the nozzle in addition to the beam. And so we're also monitoring that device. So every variable is going to be controlled for here. Now, when you combine that with the performance boost that the active speed control gives us, which is a general thing when we average it across all the different material types and thicknesses and nitrogen, oxygen, whatever it might be, this is again what we come out with, around 8%. And so what we did is we ran a scenario. This job here, 40 pieces, that's what you fit on a 5x10 sheet, 1/4 inch material cut with nitrogen, 8 kilowatt machine, 10 kilowatt machine, and then on the 12,000 watt machine, we used the machine without active speed control and with it. And I should mention, you buy a 50/30 fiber, 50/40 fiber, 50/60 fiber, 10 kilowatt, 12 kilowatt, doesn't matter. you're going to get active speed control as a standard feature now. All right, so that's one cool thing. But just to show you what it's doing, the times that we're estimating generally are too low. So we have about, like we say, an 8% increase in the feed rate. Now, obviously, we have to accelerate and deaccelerate. So what impact does that have actually on production? You can see in this case here is about 4%. So we're running this job 4% faster, not with buying more laser power, which your 8% feed rate increase is about equal to what you get from 1 kilowatt of laser power. We're not increasing the power here. We're just benefiting from the active speed control's ability to speed that thing up. So that has a really big impact on our production cost, right? And we're not even considering the fact that the laser is also ensuring that we have process reliability. So definitely it's a good thing, considering, okay, I can cut this part, takes this long, but let's kind of stretch that out to a year's worth of manufacturing. And generally what you have to consider is you're going to have things that occur, right? You're in a production facility. It's probably not air conditioned. It's maybe not perfectly clean. You have different variations of material. So we're always assuming when you say, okay, I've got a time estimate from a machine here, that this time estimate is going to be completely consistent. And the reality is that it's not, right? Because you have to consider that you're going to have a less than 100% uptime. With active speed control, we're not only increasing the speed, but we're also making sure the laser doesn't stop, right? So it's ensuring process reliability on its own. And so when we look at a very conservative estimate here, and we say, let's take that nest that we looked at and say, let's stretch that out to a year's worth of production. 1 shift, 2 shifts, 3 shifts, and see what the sheet capacity would be. How many sheets of that job could be run? On 1 shift, you can see you have a pretty substantial increase from 6,605 on the 8 kilowatt. When you go to the 12,000 without, I'm sorry, the first one is the 10 kilowatt. So your second is going to be the 12,000 without active speed control being considered. It's a big jump in capacity just based on the machine. But look at how much more material you get. 923 sheets with 3 shifts worth of operation. Again, not with actually buying more laser power, but because active speed control is just managing things on its own, as well as speeding that laser up. So based on that 4% increase that we saw in productivity, that equals to 923 additional sheets of material. And think about what you're charging your customer for that. That's a lot of additional profit that just comes free with the machine. And kind of considering that back end of the process, you have to do something with the parts. And this is a really cool new technology that's just being introduced now at FabTech, if you will. So we have parts, right? They're being kind of logged in our programming software saying, okay, this guy is going to go over to the bending operation. This guy is going to go be welded. This one's going directly to shipping, whatever it might be. So we're going to show you what we call a sorting guide today. And the sorting guide, it does a couple things. When I'm on the back side of the machine, I'm pulling these pieces out. When I snag this out of the nest, it says this is a bending part. So I put it over onto my table with bending information. This is a part that's going to be painted. So I put that over on the table that goes to painting. This is being booked automatically into our fab software. So this is the really cool thing, the party trick that the thing has. It's saying, okay, you remove these parts from the sheet, you put it into your unloading stack for your bending operation, shipping, whatever it might be. That is now in our job management software. So it's saying, okay, we know that the bending operation should have 20 parts. And let's say that you had one of the parts fall through the nest or something and somebody overlooked it. It would actually identify that. So it would show the person on the backside of the machine, who in a lot of cases is not somebody with a lot of experience, probably doesn't know the process here, that, hey, you're missing a part. You need to find that one piece. And if he doesn't go find the thing laying on the conveyor under the pallet, you're going to have automatically booked into the system a job that doesn't have enough parts. So that's flagged for the press brake operator. So a really cool bit of technology there. So what we want to do is we want to actually hop over to the laser now, and we're going to have a look at the laser itself actually running through these things. And then we're going to have a question and answer section at the end. So please do stick by. We'll make sure that we discuss any topics that might come up. And then, if we run over on time, you always have the ability to contact us as well. So let's hop over to the whole gang. We have Ian on the left, we have James in the middle, Dagmar on the right, and they're going to kind of tag team this process for us. Okay, guys?
How's it going? Can everyone hear us? How's it going, guys?
Hello.
Okay, so we're going to jump in and we're going to start off by cutting a scenario for active speed control, and then we'll continue going on from there. So we'll move right over to the machine and begin the process, and we'll explain it as it's going on.
I apologize. Everybody had to look at my stupid face a little bit longer. I couldn't figure out how to turn my webcam off. So now we're seeing your control. Everything seems okay there.
Okay. Excellent. And can we see inside the machine as well?
Beautiful.
Okay, perfect. All right. So I'm going to bring up the screen here. It's going to start the program. So what I've done here in this scenario is we have 3 different thicknesses of material in mild steel. It's going to be 16 millimeter, 15 millimeter, and 14 millimeter material, but I'm cutting it all with a 15 millimeter tech table. So the machine is automatically going to adjust the speed based off of what it's seeing during the cut. And if you can see on the screen here, this is actually looking down into the cut right now. And what the sensor is doing is looking at this different levels of light that is shown in here and determining whether or not it can speed up or if it has to slow down based off of the shadows that it sees coming in the process. So you'll see as it's going in now, it's going to slow down because now we're into 16 millimeter material. As it comes back around, we're going to go back into thinner material. It's going to speed back up. And this is an extreme circumstance here, but it really shows the point of what the technology is actually doing during the process.
Wait, hold on, Ian. So you're telling me if I buy a 1/4 inch nominal material, it might not actually be 1/4 inch? That's ridiculous.
Yeah. Yes, that is true. So we all know in the sheet metal industry, our vendors can shift and change, and somebody's way of measuring thickness might be a little bit different than somebody else. And this allows us to compensate for that automatically. So your operator no longer has to go in there and change that portion of the tech table. This will also compensate if the material grades are slightly different. If the cutting conditions can't be optimum, it's going to slow it down to try and adjust for that. So we can see on here, we had a change in the feed rate. At one point, we were almost at 112% feed rate once we go into the 14 millimeter. Let me pull out a part real quick so you can see.
Sure. While you're doing that, maybe I'll ask you, I saw on the control, and I'm sure everybody in the audience saw this too, there was a little readout that said focal diameter, and that guy went from like 210 micron to, I think I saw like 900. What's going on there? What's the change in the focal diameter?
So that's actually piercing into cutting. So you're not necessarily going to be piercing with a 900 millimeter or micron beam. You're going to be piercing with something thinner to get through the material faster.
So, folks, I apologize. Ian's a Harley rider. I'm a Ducati rider. This is why I understand a Segway better than he does. The large beam diameter you saw was bright line fiber. So the cool thing about bright line fiber is that it gives us an enormous beam diameter range. So when we're cutting in this oxygen range, we want to be able to make a much larger laser beam. And so rather than being kind of restricted like you normally would with a fiber laser to a pretty small focal diameter, so you use tricks, collimation in the cutting unit or shifting the focus lens, we actually change the mode and the beam on the fly. So you get a much bigger beam and you do so much more quickly, and you get the sort of quality that you see there burn through Ian's glove.
Yeah. So we have 14 millimeter right here. And then hold on one second. It's hot. And then this is actually 16 millimeter, all cut with the same tech table. You can see the machine was able to adjust for us and cut those 2 different tech tables, or 2 different thicknesses, the same tech table, and we were able to cut them without issue.
Yeah, it's definitely impressive. And this is
nice
kind of, yeah, I can imagine it is warm. And this is kind of this is the future of development that Trump want to take. So what we want right now and what we achieve is controlling for, of course, the feed rate. this is just the first step. So we really want it to become like kind of self-contained. When the laser's cutting, hey, laser just sort things out, right? So not everybody has knee in here to be able to kind of tweak tables in and whatnot. So the machine's extremely important, especially going forward into the future when more expensive labor markets like we have in NAFTA are trying to compete with cheaper labor markets. So the laser is becoming more and more adaptable. And with the continuing development of these processes, we really want to get to the point where the thing just does it on its own. Says, I'm cutting now, I'll adjust all the other relevant parameters outside of just speed. So this is just kind of a jumping off point for us. All right, so what do we have next?
Okay, so now we're going to jump into some cutting 1/4 inch. And while we're doing that, it's going to change nozzles for us. Now, we've created a scenario where it's going to first look at a nozzle that's no good. And with the smart nozzle automation, it's going to take a picture of that nozzle, and it's going to determine that it's no good. Now, we have another good nozzle in the nozzle changer, and it's going to automatically change over to that one and begin the cutting process. So we'll go ahead and jump right into that. Sure.
So that's an important part of the true automation, right? So we're sorting the cutting process with active speed control, but let's say you have a tip up. The machine has to be able to make sure that your conditions are still good. So on all of the Trumpf product lines, not just the 5 series fiber laser, we have 360-degree collision protection. So if you hit it from the side, you hit it from the front, we can stop that motion unit in, what is it, 15 milliseconds? It's incredibly fast to the point where you probably wouldn't even see that there was a collision, but it was able to respond. And so the thing you have to consider is, did I damage the nozzle? And if you damage the nozzle, of course, it needs to be replaced. So this is capable of taking care of that on its own.
So the first motion it's doing, it's actually checking the ASC, the alignment of the beam right now. After that, it's going to go over to the nozzle camera and take a reading of the surface of the nozzle.
So this is checking beam center?
Mm-hmm.
Perfect.
So now it's going over, and it's actually taking a picture. And it's going to determine whether or not the nozzle is good enough to use.
So even with the 3-piece nozzle, the camera is capable of identifying if the sleeve's bad?
So it sees that something's wrong with the nozzle. It's going to try one more time to make sure. This is a really nice feature if you're going to be planning to run, say, automation overnight. You would put multiples of the same nozzle in there, and then if there was any issues with collisions or anything like that, it would check the nozzle. If anything went wrong with the nozzle, it's going to switch over to one that it knows is still in good standing. So now it determined it's no good. It's going to go and grab a new nozzle. And then after it begins cutting, I want to show you another feature on the machine that's really nice, what we call parallel to production nozzle changer. So while it's actually cutting, you can pull the nozzle changer out of the side of the machine and replace any damaged nozzles without interrupting your cutting process.
So what is it that triggers the nozzle check-in?
So there's different settings that you can have in there. We have it set up right now so that before it uses a nozzle, it's going to go ahead and check it. But you can also set it up for a certain amount of pierces or collisions or timing.
Okay.
So if you see on here, we actually see the surface of the nozzle that it read that it decided was no good. And we actually can see the indentations in there. And I can pull that nozzle out for you, and you can see I actually took a file and cut into the nozzle so that we could see an extreme case. Okay, so now it's jumped into the cutting process. So if we go to the outside camera real quick, I can actually pull this out while it's still cutting. Now it was this nozzle that was no good. I can pull that one out and put our new nozzle in. And then we tell it that it's reset. Now I don't know how close I'll be able to get this in here. But if you can see, there's actually weird marks on there. That's where the file cut into it. And that's what it was picking up on the screen. Okay. And so now that I've shown you that, James is going to talk a little bit about the cutting program that it's doing right now.
Okay, hey guys, so hopefully you can see our screen here on the inside, and we see the machine is moving around, cutting our parts out. But you'll notice that it's doing it in a really specific way. What we are doing here is a special programming technique and cutting technique called smart collision prevention. Basically what this is it's an algorithm in our TrueTops Boost software that allows the machine not to crash. It looks at all the parts, all their placements on the slats, where all the lead-ins are, all of that stuff, and how they're going to fall and tip. And then it creates a cut path that allows the laser to cut all the parts without crashing into the cutting head, and it also can take into account the automation system that you have. So not only is it not crashing our machine, but it's also not crashing our automation. And what this allows for you to do is to do a lot of dynamic nesting without worrying about crashing the machine, or is this nest going to work, or is it not going to work, or do we have to watch it, or anything like that. You'll also notice some other features that it's doing, specifically scrap cuts. It does those in a different way than we're used to. It's actually doing some right now, where it actually will cut the scrap cuts and then move around and cut each piece away. And always it moves away from the tipping part so that it doesn't crash. You see it's doing some other stuff. It'll cut certain contours partially, like right there. It leaves a big tab on the material to then cut it back at a later time when it's safe. When it knows that it's safe, it's not going to cross back over that path and crash the laser head. Some other stuff that's going on right now. So I don't know if you guys can see too closely, but we're using a special nozzle as well. During this cutting process, we're using high-speed eco. That is our special nozzle technology. It's a touchdown nozzle, and I'll actually stop the machine right now, and we'll pull a part out, and I can show it to you guys. What this does is it allows us to cut about 2.5 times faster than our standard single orifice nozzle. It also saves gas, up to 70% over your standard kind of table nozzle. And hopefully you guys can see the side edge here. It's a really nice looking part. So there's the top of it. There's our bottom. Really nice looking. We don't really have any dross or anything like that. It's cutting at 482 inches per minute. It's using nitrogen. Awesome.
And so with that really low pressure and consumption, then that's how we're capable of getting away with compressed air cutting, without having like a compressed air generator.
Exactly. So this allows you to not only just cut effectively and efficiently with nitrogen, but allows you to do some other special things. Like Brett was saying, you can utilize air. This cutting technique is going to use a low pressure. 4 to 6 bar is what we're typically seeing with our pressures, and that's kind of what's allowing us to get away with using a lot lower volume of nitrogen. And the nozzle design itself is encapsulating that nitrogen as well. So it's not letting it blow off into the environment. It's pushing all of it through the kerf, allowing for a really, really nice looking cut because you're containing all the gas and efficiently pushing it through the kerf. But again, also allows you to contain all of it in that sleeve. And in conjunction with the low pressure, allows you to have a gas consumption around, what is it, Brett? Around like 1,200 cubic feet per hour.
Yeah, that would be worst case scenario. I think quarter inch is 1,100 and change. So it's very, very low consumption. It's interesting.
Yeah, and you can...
Go ahead, my friend.
So what's really cool about this is you can use the nozzle technology for a wide range of materials. On this machine specifically, 160 thousandths of an inch steel, up to 3/8 or ½ inch if you want to go really crazy. And then in stainless steel, 160 thousandths of an inch up to 1 inch. So you're using the same nozzle for all of those different things. You're using a low pressure gas, and you're getting great quality parts. And again, you're going really fast. You're going a lot faster. You're able to pierce really fast and cut really fast because of that special nozzle. So really, it's kind of like a Swiss Army knife, I guess.
And I would say, one of the important things, so the idea of like encapsulating the gas so it goes through the kerf rather than over the surface, like that's not new, right? That's not what's unique about high-speed eco. What is that it's what, 10 millimeters away from the surface about, and I might have my exact distance wrong, but you have almost like suspension. So that sleeve is a consumable item. So that thing will last about a shift. The upper portion of the nozzle, that thing can last, indefinitely. And that's the beauty of it. You can see that James is being really aggressive. Like it's just pounding down into position during pierces. If you were cutting actually like a diamond tread, the laser would have no issues with it. Corrugated material, the laser has no issues with it. And so the beauty of the high-speed eco is, yeah, exactly, that little guy allows us to deal with non-flat surfaces. And that's usually the difficulty with nozzles that have really, really shallow offsets to the surface. That's how we're able to solve that issue.
Yeah, so you guys can see here, the sleeve right here kind of moves up and down. Pretty sweet. See you guys again. You can see that sleeve moving up and down. Really awesome nozzle technology.
The only complaint I have here is it cut that sheet a 1/4 inch extremely fast. It's actually done right now.
Yeah, and with that, I guess we'll go to my other colleague, Dagmar, and have her take you guys through the next step here.
All right. Thank you, sir. Dagmar, welcome.
Hi, Brett.
Hello.
Can you hear me?
We can hear you just fine, and you have to be nice to me now because
Perfect.
we have an audience.
Okay, so basically, Brett already talked to you a little bit about our last point that I would like to highlight here. It's our new option, the sorting guide. The sorting guide is basically a camera-assisted sorting help for after we have cut our sheet. This means we have here our cut sheet, and here I can see what I have here. How you can see, I have it grouped into different next stations where it has to go, like painting, shipping, press break, or trump. So you could sort it in a way whatever you want, like different assemblies, or if you want to make it to different customers or different follow-up processes, basically. How you already see, we have here for our first part in painting, it has this little red 1 on it, and also here our trump part on the bottom, because it already detected that one part that I took out while James was talking and showing you then the edge quality, and we had here a little tip up basically, so this is a part that potentially fell down while we had our palette changer. So when we now start taking out parts, you will see on the screen how it will select only those parts that are basically are belonging to the same group. So here I started now for the parts that I want to send to shipping, and you can see now those parts are missing on our screen. So the parts that were already removed and the parts that I now removed basically. And when I go on like this, you will see how one part after the other will disappear from the screen. And now you might think, okay, I'm only one person, but what if there is like a second person that helps me taking out parts? So when I just start taking, there was the same group, awesome. I could watch the screen. So just start taking it from another group. You see how that additionally gets then colored up. When I complete a group fully, you always see how I get those little check boxes also when I have taken my parts. And so I can basically go on with the whole sheet. It's also really nice when I have, for example, two really similar parts, like the trump part I took. I have it once in blue, once in orange. So it shows me exactly, hey, you're still missing one from the orange group, that I can grab this here and have them all out. Come out. So. And now I stop at this point and just want to quick show you on our control in the front how we then can also organize or tell it when we would have, for example, accidentally a part scrap or something like that happen. So this is our screen, and then we have here the booking. So here in the booking, I can now say, okay, I retrieved that one blue Trump part that I had taken earlier and I put it to my other parts. So we have them all here, and we have a nice green, easy to read checkbox that they are all here. Then I'm like, oh, where are all my shipping parts? So maybe, for example, I had scrapped one, so I also can tell my system if I had one that got lost or accidentally bent up or things like that. And when I have them all booked into my system, I can here say, finish my sheet, and it reports it back to our TrueTop step system, and we know how many parts we have or what we are missing. Okay, that's it from our machine for today, Brad.
Okay, thank you very much, Dagmar. So that's really cool because Trump is really putting a lot of focus on Industry 4.0. So if we're looking at scenarios where we have a lot of interconnectivity on the machines, all these lasers and press brakes and punches, for that matter, have an OPCAU interface. So the machine's capable of gathering data and sending it out. So it could be data that is stored within your own MES. It's going to be a little bit more limited. You also would have some information that could go back into a software like our Fab software. It's really cool from the perspective of us really being able to control it and have a good overview of your manufacturing processes. So thank you, everybody, for your great support. You guys do all the hard work. I'm sitting in an office over here just kind of enjoying myself. So we're going to hop over and do some questions now. I'm going to field the questions. Since I probably don't know the answer to most of them, we're keeping our experts on hand. And so if I can't answer something, we certainly will have somebody who will be able to for us. And I have to say I'm shocked. I don't see any questions so far. Now, surely somebody has a question, right? I understand if you're totally overwhelmed. You said, oh my goodness, I've never seen such amazing technology and such high cutting speeds that, you might be a little bit shell shocked now. But I'll give you a moment to maybe catch you up. And while I'm waiting for questions, I'm sorry. Did somebody say something? No? Okay. So, maybe while we're waiting for potentially some questions to come in, what I think is really cool about, kind of looking at the relationship of the sorting guide, taking the parts off and putting those into a specific location. What's interesting about that is we have a technology called track and trace. The track and trace allows us to basically know based on, triangulation. So we'll have little sensors in the facility. The more sensors you have, the more accurate the identification of where the actual parts are. So Dagmar could have been taking those pieces off, putting them onto a table that has a track and trace. So right away, the software, the TrueTop's Fab will know jobs booked. We actually not only know that the job's done, but even where it's at, and even whether the process is started over on the press brake or whatever it might be. And related to the smart collision prevention James had shown us, Trump is really unique in being able to integrate our cutting systems, our lasers, our punches, our hybrid machines into really good bending automation. And unless you have like a punch laser combo, it can be kind of tough to sort those pieces out because you have to say, well, I have to be worried about the potential for tip up. So typically you're tabbing the pieces in. By going with a system that has the smart collision prevention, we can actually avoid the necessity to do tabbing, which is pretty awesome. Oh, so I'm seeing some questions pop in. All right, so bear with me because my screen is showing this very, very small. So maybe I can expand this. There we go. Okay, so one question we have, what kind of assist gas pressures do you need for nitrogen on thicker, let me expand this, stainless or carbon? Dagmar, go ahead.
The question
Did you hear the
how
question?
thicker is thicker? Yes, no, I mean, how much thicker is thicker, basically? So when we go in really thick.
Hold on, my friend. So the question is, what kind of gas pressure do you need to do thicker stainless or carbon? So let's say once you get into, well, let's discuss carbon. So let's say up to where you go over to oxygen, right? So at what point would we switch to oxygen from nitrogen on carbon steel with a 12 kilowatt?
For sure, after half inch.
So half inch, okay. And what sort of pressures would we have in half inch for gas pressure?
1700 psi. Oh no, wait, it's the cubic feet per hour. What is it in psi, my friends? It's 8 bar on a machine roughly with the high-speed eco nozzle. I'm German. I don't speak psi. How about James takes psi question?
Right. James is a computer. He has a conversion calculator in his head. How many psi is that, James?
Yeah, so basically what we're looking at when we cut the thicker carbon steel like that, like Dagmar said, like 8 bar, like 6 to 8 bar. So there you're looking at around 80 to 110 psi, maybe a little bit more. But that's about what you're looking at there. So it's fairly low pressure for the carbon steels. And then when you get into the stainless steels, it's actually even lower pressure. You're at around 4 bar there, and that's going to translate to, that's around 65, again, 75 psi, somewhere in that range. So it's really low. You're not going to have to have a huge nitrogen system to deliver a ton of pressure to this thing. That's an awesome part about it. And again, with air, you can utilize the current compressor systems that you have. You don't have to go to a fancy compressor or anything like that, a high pressure compressor or anything like that. Your typical shop compressor can supply the air if you wanted to cut with air in the stainless steels or in the steel, because you don't have that pressure requirement there anymore. It's a much lower pressure. So.
Great. And so we've had stainless steel tables for compressed air for a while now. Now we have the steel tables, right? So that's a little bit newer. So if you buy a machine, rather than having only the tables to cut stainless steel with compressed air, now you also have the tech tables to cut carbon steel with compressed air, which is, I think, probably a little bit more practical for our customer base. So that's a pretty exciting thing. So, yeah, definitely. And, you software gurus, feel free to correct me here because I'm, potentially wrong about this. But so we have a question about smart collision prevention being a boost feature. Now, the question is whether, that is proprietary to Boost, and it is. It does require the Boost software in order to, utilize the sort of algorithms we have on how to hop around and when to tab, when not to tab. It actually is always going to try to not tab unless it needs to. But there is also something in the code, right, where, our code is not just G code. There's a little bit more in the structure. So there is a machine portion of it, right? So we have we have smart collision prevention from a software perspective, but the machine does also have to support it.
Correct.
Mm-hmm. So I'm just kind of scrolling through here.
But Brad, maybe a nice fact about smart collision prevention is that our other software, Metamation, is also offering a smart collision prevention. It's just a bit a simpler version. In Boost, you can set some settings and adjustments in the background for if you want to have more scrap cards, or if you don't want to scrap cards and more for tap whatever you want. And Metamation is basically more automated version where you can't set those settings, but it is also having this option.
Oh, good. I actually didn't know that, so thank you very much for that, Dagmar. So I think here's another interesting question. Now, when you're using the high-speed eco nozzle, we know that the sleeve itself is 8 hours worth, right? That's about how much we can expect to get out of that thing. Over the course of time, is it possible for that to have like a little buildup of slag? Let's say you have like really dirty material. Is there a potential for anything to get kind of, I can't imagine inside the nozzle, right? But maybe on the outside? Do you ever have an issue with anything sticking to that sleeve?
The issue you would have is if you had some sort of failed cut, but nothing really attaches to the sleeve. The issue with the sleeve is that it's actually riding on the material, so it's slowly wearing away.
Mm-hmm. And if it wears away, then the gas escapes, and I think that's the issue, right? So, and
Correct.
The whole idea here and why we get so much higher cut speed is because of the same reason we get a lot lower consumption. It's because, usually when I'm chopping my way through this material here, you have with a normal nozzle a relatively large offset, and that's kind of what you want from a reliability perspective and a safety perspective. But with a fiber laser, you have that really high energy density. It's very efficient coupling with the light or with the material. So compared to like a CO2, a lot less of this light bouncing off the surface. It's a good thing. The bad thing is, from a general perspective, when you're cutting with nitrogen, that kerf is fairly narrow, so you have to use a ton of gas to get it through. So that's usually kind of what your threshold is with just a normal nozzle technology. And that's why you see not just Trump, but pretty much everybody, in order to be able to get more speed out of this thing, you try to get all of that gas through the kerf efficiently. And that allows not only for, cleaner material, but that's where you get the higher speeds. The beautiful thing about the high-speed eco is that, it gives us kind of the best of both worlds. So it's pushing all the gas through the kerf. Very little, if any, actually escapes, unless, like Ian says, you start to wear it out a little bit. Like, for cutting like checker plate, a diamond plate all day, you're going to wear it out quicker than normal. So you're definitely going to have a wear expectation for the thing. But the cool thing about it is, again, you have a really large offset, like Ian showed this. So that's kind of like a little bit of suspension. So you don't have to worry about smacking into it. So you don't worry, like, when you're doing thicker material like this, you get like a slag bulging. You don't have to worry about that because the nozzle is just going to ride over it rather than running into it. We also have what's called high speed. So high speed is similar to eco as far as like the edge qualities and the speeds are concerned. It's going to use a little bit more gas. It's still a low pressure process, but since it's stabilizing the gas, but still a lot of it's going to go off the surface, you're going to be using more gas than you would with eco. But that is a decent alternative to that as well. Okay, so let me just kind of look through here. So we have a question about the sorting guide and what categories to use. Is that from the programming software? And the question for that is yes. So that's going to be associated through the job management and the fab software. And since Dagmar is kind of our resident expert here, I'll let you answer kind of how that's assigned. It's through the software, yes?
Yes. It's basically the information or the part information you can additionally put in the software, like if you would assign it to assembly or you give it to a customer or whatever your criteria might be, basically. And on the machine control, then you can select which criteria you want it displayed sorted for, basically, then. That's a little filter, like a normal filter thingy you use in a software that you can set that which ones you want.
Okay. And so it's kind of based on what your configuration is in fab, right? So I might have 3 press brakes. And so I've got my 5130, I've got my 7036, I have bending automation. And so you can identify like the individual stations, not saying this is a bent part, this is a painted part. It's associated with that step in the job, right?
Yeah. Okay. That you can basically then associate with the workflow. What would be the next step in the workflow? And then you could already also designate which press brake it is, because you probably already have created your programs for the press brake then also. And so it's automatically then basically in fab, it's been automatically assigned where it has to go next. And you can filter for that here too. Yes.
Okay, great. Thank you. So we have a question, and maybe there's a little confusion here. So it said early on in the discussion, you'd mentioned that 8% speed bump per kilowatt in a quarter inch. Is this a safe general rule of thumb from 8 to 10 and then 10 to 12? Now, bearing in mind that generally you get about, let's say, 7 to 8% per kilowatt, as you'd mentioned here. But then when we're talking 8 to 10 and 10 to 12, it's about double that. So we saw on the chart that we're actually seeing from 8 to 10 is in the 20s. So between, I'd say, if you were to average it from the biggest gains to the smallest gains, it's around a 20% for 2 kilowatt. And then 8% would be the average feed rate increase that we saw from, if you go to our smart factory in Chicago, I imagine a number of people have been there. This is a little different than we have here. So in the facility where we're all located in Farmington, Connecticut, we're building the whole range of machines here. So literally from the ground up, our 1030, 1040, 2030, 3030, 3040, 3060, 5030, 5040, all US products, as well as some automation components. They're all being built up from the ground here. And then over in our building where we're all sat, this is a demonstration area. So we don't really run, production for customers, and the production we run is relatively small. So we get a lot of good data from the smart factory because they're actually running production for customers. And so they, of course, utilize a lot of the new technologies that come out. So they've been using active speed control as well as, some of our customers that have it. And so we asked for feedback. What do you generally see as the benefits? And, in a lot of cases, people say, well, these things cut pretty reliably. We're not so worried about losing parts so much, but we always get a note on how big of a boost you actually get in the feed rate. And what we saw for quarter inch from our smart factory in Chicago, and as well as some customers, is about 8% in the quarter inch material. But then again, you have to consider that you have to accelerate and deaccelerate. So in our production example, we saw about a 4% boost in the actual job processing time.
So Brett, we probably have about time for one or two more questions. Okay. So see if you can find some good ones in the stack.
Oh my goodness. Now I really feel like I'm under a lot of pressure. I'm going to choose the worst question. Like what's your social security number? Something like that.
Well, let me ask you a question. Something we touched on in the beginning is that active speed control is really trying to work with material conditions that it sees. Let's say I'm somebody, though, that doesn't worry about the quality of my material that's coming in. It's really consistent. It's homogeneous. It's job to job, lot to lot. Is active speed control for me?
Slay, I kind of missed some of your question. Can you say that again? I couldn't quite hear.
So I'm curious, if I have consistent material quality, every job that I'm running, and we've talked on how active speed control, one of its features is that it's overcoming some of that variability. But if I'm somebody that has good quality material, does that mean that active speed control is not for me?
Oh, certainly not. And, like I say, the feedback we've generally gotten from customers is that, yeah, it's cool that it will control for bad materials, but the laser, especially with bright line fiber, is so good at doing that already because of, the massive beam it produces in the materials where it's more likely for issues to occur. Nitrogen cutting is usually pretty reliable. So what people are saying is that it's great that it controls for any of these issues that might creep up, but they're probably not going to. But what will absolutely happen is you'll get a benefit if the laser increases its feed rate, and that happens very consistently. Now, if you had, let's say and I think this is generally the way the thickness variations go, but let's say you ordered quarter inch material and it came in closer to 5/16. We're never that lucky, but in a case like that, yeah, it's good that it's compensating to make sure you're not just welding the parts into the sheet. And you might lose some of your cut speed benefits, but usually what you're getting is that average increase in feed rate. And like we say, in this particular material thickness, we're talking about 8%. And so even if you have perfect material and you've never lost the cut, great. You're going to get a really big increase in the amount of throughput that you have, because when we develop tables, so if I'm a customer, I say, hey, Trump, can you tell me how long it takes to cut this part? Nest it in with this piece. And we send out a time estimate. They're, pretty, I'd say conservative. Not even conservative. We're just using what we think is going to happen in production. So we use the actual values that are in our Boost software with, reliable processes. So actual head retractions, lead-ins when they're needed, those sort of things. So we don't, kind of get overly aggressive on the processes, but it's still worth noting that if I have a time estimate on a 5 series fiber laser, it's probably slower than it would be in reality, because most likely it's going to push the speed. It's going to do that on its own.
Yeah, I would also add that it doesn't necessarily just compensate for material. If, say, your beam centering is starting to change or something, maybe you had a collision, it's also going to compensate for that as well. So you can continue to get through the process and not actually lose the cut during that process.
Yeah, excellent.
So cut loss prevention.
Yep, definitely. It's cut loss prevention too, and if a condition changes. And the important thing to note, the reason that Trump goes with a disc laser for a situation like this is not just it's a much more reliable source, but we also have the ability within our closed loop measurement system to ensure we're never going to see fluctuations in laser power plus or minus 1%. So if I buy a 12 kilowatt laser today, 5 years from now, plus or minus 1%, 12 kilowatts, doesn't vary. So as long as you're controlling what's happening down at the workpiece, what's going on the surface here, there's just I mean, the world's your oyster at that point because you know the system's going to be consistent. So now we're actually controlling for the things that normally you can't control, which is the material. That's your biggest variable. All right, and I think that covers it today. So, and you know, I begged for questions, and then boy, did I get them. So, unfortunately, we've run out of time. So, if I didn't answer your question, please do reach out to us. We'll make sure that we all get on answering your questions as soon as possible. And yeah, we look forward to talking to you in the future. Thanks, everybody.
Thanks again to everyone, all of our guests.
Thanks.
We wish you well. We see you soon.
Goodbye.